Hey guys, this is Miss Fantassel. So I wanted to go over some of these example problems with you for exponential functions and models. And so I really want to just for a second go through the introductory section, just because I think it really does capture the idea behind exponential functions. And so it says, today is your lucky day. You've just won a contest and they can pay you your prize in two different ways. So option one, they can pay you $10,000 every 10 days for 30 days. Or option two, you can have a penny that doubles every day for 30 days. So let's just kind of see what happens with option one so that we can make our best decision. I think that most of us would think, oh, I'm going to take $10,000 every 10 days, but because it does sound like it's more than a penny, but let's just kind of see what happens because I do feel like this might be a trick. So if I take option one, then the first 10 days I'll have 10,000, and then in 20 days I'll have 20,000, and in 30 days I'll have 30,000. I would be happy with that. But let's see what happens when we have a penny. So when we start with a penny. So day one, I would have 1 cent. This is not working very nice for me. Okay. And then day two, 2 cents. Day three, 4 cents. Day four, 8 cents. I'm just doubling my previous amount. 16 cents. Day six, 32 cents. Day seven, 64 cents. Day eight, $1.28. Day nine, $2.56. Day 10, 5. So day 11, 10.24. Day 12, 20.48. Day 13, 40.96. Day 14, 81.92. Day 15. All right, I'm going to speed this up for us. All right, so I'm going to stop here. I stopped at day 23. So already by day 23, I have $41,943, which is more than if I had taken 10,000 a day. And so you can see that taking a penny and then doubling it every day would actually give us more money than if we had taken the $10,000 every 10 days. Now, it's not always the case. If I was only taking for 20 days instead of 30 days, then it would have been more beneficial for us to have taken option one. But because our penny is growing so fast, it's growing much faster than our $10,000 is, which means that over a longer period of time, we would make more from our penny doubling. Okay, so the form of an exponential function, it looks like this. So f of x equals a times b to the x. And so just a couple things about this function. A is your y-intercept. It is also your starting amount. b is going to be the base of your exponent. It's also going to be your growth rate. And then using exponential properties. So just from our example with the penny, and let's go back. The x is going to be your number of times that you're growing your function. So usually it's time, but it's not always time. And so using exponential properties. So in our example from before with the penny, the way that we would fill in our exponential model is our starting amount would be the penny that we're starting with. And it's also your y-intercept. So our starting amount was our penny. And then we were doubling it every single day. So our growth rate was 2 because we were multiplying by 2 every single day. And then you'll notice this, so this exponent looks a little bit different than the one before. You'll notice the 7. And the reason why is because our initial model was looking at the $10,000 per week. So the x in this case is the amount of weeks. But we were doubling every day. And so that 7 comes from the amount of times per week that we were doubling. Okay. And so exponential functions, I know you guys are always asking, like, when am I ever going to use this in real life? And exponential functions is one of those units that we actually utilize this in everyday life, and we're actually utilizing it right now in our pandemic. So exponential functions looks at growth and decay, and you may have heard those terms in your science classes. But an example of exponential growth would actually be like right now. So the growth of a virus is exponential growth. And the reason why is because we have one person, and let's say one person spreads it to every 2 people. So this person will spread it here and here, and then this person's going to spread it here and here, and here and here. And so you'll see that it started with one person, and then there was 2 people, and then there was 4 people. And so I'm multiplying by 2 every single time. So yeah, so the growth of a virus is definitely one where you would see exponential growth. Growing bacteria, compounding interest, population growth. So these are all areas where we would use growth models. For decay could be depreciating. So if you see the word depreciating, that means that it's decreasing. Like if I buy a car, the longer I have that car, the less that it's worth. And so that is an example of decay. Like temperature or cooling many times can be used with a decay model. Decaying matter. And so another formula that we use quite often in exponential functions is this one right here. So f of x equals p 1 plus r to the x. Sometimes they use different letters, but this is what your course used, so that's what I'm going to use. And so this is the exponential growth model. Our p is our starting amount still, so that's the same thing as like the a in the last equation that we looked at. Sometimes, especially if you're referring to money, it'll be the principal. So if you see that word principal and it's not spelled like Mrs. Moon principal, it's like L-E at the end, right? So the principal amount is also your starting amount. And then this is a 1, not a variable. R is for our rate. If your function is increasing, then you're going to have a positive rate. If your function is decreasing, then you're going to have a negative rate. Okay, and the rate, you always want to write it as a decimal, not as a percent. So a lot of times they'll give it to you as a percent, so you want to make sure that you're changing it to a decimal. And then x is going to be usually our time. Make sure that you're consistent in your when you're looking at the time. So if your rate is in weeks, then you want your time to be in weeks. Or you're going to have to do like we did with the pennies and maybe multiply by something in your exponent so that you have the right units of measure. So Paula puts an initial $100 into a savings account. The account has a 3% annual compound interest rate. Create the function that models Paula's savings account. Use that to find the amount of money in her account after 5 years. So we're going to use the p 1 plus r to the x. And so I'm just going to kind of go through and read. Paula puts an initial $100. So initial tells me that that's her starting amount. So Paula is starting with $100. That's her principal. The account has a 3% annual compound interest rate. So here's where they did tell us that it's 3%, and so they gave it to us as a percentage, but we don't want to put it into our function as a 3 because that would actually be growing 300%, which would be a crazy amount, and they are not going to give you that much money in your savings account. So I need to convert this the way that you convert it. So here's our decimal place. You're always going to move it to the left 2 places to change it to a decimal. So 0.03 is our rate. And in this case, she is growing her money. You don't put your money in a savings account to lose it. So her money is growing at 3%. And so that is a positive 0.03. Create the function that models Paula's savings account. Okay, so that's my first direction, is to create that function. And so I'm just going to stop there and make sure that I'm answering every piece of this question. So with the information I have so far, I have f of x equals 100, and then 1 plus 0.03 to the x. And I'm just going to simplify this a little bit. So I'm going to add the 1 and the 0.03 together. You cannot simplify it more than this, so please don't try to multiply the 100 and the 1.03 because that exponent is in the way. So you cannot multiply these two together right now. All right, so now we have a function that will model Paula's growth for any amount of years. The percentage was an annual interest rate, so our time is in years. And so we want to specifically know how much money is in our account after 5 years. So I can take that 5 and I can plug it in to my function. So f of 5 equals, you want to make sure that you're replacing x in both of the x's. And that just helps me to keep track of her input and her output. So this is my input of 5 years, and then whatever this is when I work it through, that's going to be my output. So writing it in function notation just helps us to keep track of what input goes with which output. And so I can plug that right into my calculator. If I'm not plugging into my calculator the whole thing, then I would need to do my exponent first, so make sure you're following orders of operations. So 1.03 to the 5th. I'm going to write this out just for those of you that can't plug the whole thing into your calculator. You'll notice a really long number. You want to keep it long while you're going through because you don't want to round too many times so that it's inaccurate. So write this number out kind of long. So we get 1.1592741. That's probably good enough. And then times 100. And so f of 5 equals 115.927. Now, you always want to ask yourself what you're dealing with because that's going to help you to figure out where to round. So I'm finding how much money she has in her account. And so we don't have anything less than a cent, so I'm going to round to the nearest penny in this case. If I was dealing with people, I would round to the nearest whole number. So you always want to make sure you're paying attention to what the context of the problem is. And so after 5 years, she'll have $115.93 in her savings account. Okay, graphing. I know how much you guys love to graph. So let's look at the graphs of growth and decay together. What you'll notice about growth graphs, and so we still have this like a times b to the x equation. But then over here it specifies, so for growth graphs, your b is always going to be bigger than 1. So notice I have an example here where my base is 2. So 2 is obviously bigger than 1. This is going to be a growth graph. With decay, I have the same exact equation, but this time my b is between 0 and 1. It doesn't include 0 and it doesn't include 1, but it's somewhere in between there. So some kind of fraction less than 1 or decimal less than 1. And so if you have one of those, then it's going to be a decay function. And so for our example, I'm using 1/2 to the x. All right, so let's come over here to the exponential growth function. And so I just kind of want to see the behavior of what's happening. Notice on my coordinate plane, I don't have any tick marks. So if you don't have any tick marks, then it automatically, or if you don't label them, then it automatically goes by 1. So I'm not going to label it just because I want to save room. If I was going by something else, like maybe 2s or 3s or 4s, I would have to label my tick marks. This is x, this is f of x, which is the same thing as y. And so just to kind of see what happens, I'm going to pick some values, some negative, some positive for this function for my input. So I'm going to use -2, -1, 0, 1, and 2 for now. And I'm going to start with the easy ones. So let's start with if I plug in a 0. So if I plug in a 0 for my x, 2 to the 0 power, and I talked about this in the first video that I posted. So 2 to the 0 power, or anything to the 0 power, is just going to be 1. If I plug in a 1, so here's my input of 1. If I plug a 1 in for my exponent, 2 to the first power is going to be 2. If I plug in a 2, 2 squared I know is 4. And so I know that we get a little bit tricked up with negative exponents. I did talk about those properties on one of the previous videos, but just in case you forgot, so if I plug in a -1, I'd have 2 to the -1. What can help you remember? So if you look at my y values, I went from 1 to 2, from 2 to 4, and so I'm multiplying by 2 every time. If I was to work backwards, then I would be dividing by 2 every time. And so 2 to the -1 is just the same thing as 1 over 2. And 2 to the -2 is going to be 1 over 4. Got these points to see what happens. So -2, 1/4 is like meh, right about there. -1 to the 1, or -1 1/2, right about there. 0, 1, 1, 2, and then 2, 4. And so when I connect these, I could have smaller values for x. I could have kept going on the left side. I could have kept going on the right side. And so there are arrows in both directions. Our function's never going to get negative. So you notice that when I have an exponent of 0, my y value is 1. And if I had an exponent of a negative number, then my y value is a fraction. So my function is never going to reach 0 as a y value or negative as a y value. So we have this like line right here. It's not actually part of my function, so I draw it dotted. And it goes over the x-axis, and that line is called an asymptote. And so the asymptote is a line that your function gets closer and closer to, but doesn't actually cross it. And so it'll just kind of hug that asymptote on the end. Okay, so looking at my domain, remember, is all of my x values for my function are all of my inputs. You're looking at your graph from left to right. And so this particular graph goes all the way to the left forever and ever. I know it looks like it stops at -3, but there's an arrow here. It keeps going. And so negative infinity is all the way to the left. Remember, we don't put equal to's with infinities because it's not an actual value. It's more of like an idea. And then my variable for x, or for a domain, is x. And then how far to the right does the function go? Well, if we follow this function, it goes to the right. There's an arrow, so it goes to the right forever and ever and ever. So you can either write it like that, or you can write all real numbers. And then I also showed you guys that symbol with like the double R. And so any of those answers is correct. For the range, now we're looking at like how far down the graph goes and how far up the graph goes. So how far down does this graph go? Well, if I keep going, and I just keep getting closer and closer and closer to 0, but it doesn't actually touch 0, so I'm going to write a 0 here because I'm getting as close to 0 as possible, but I'm not going to put an equal sign with my inequality. And then range is f of x in this case, or y. And then how far up does the graph go? Well, it goes up to infinity forever and ever and ever. The y-intercept, so just to kind of refresh, the y-intercept is where the graph crosses the y-axis. And so it crosses the axis right here at that point, 0, 1. Let me use the different colors, you can see. Okay, and so let's come over to the right. Now we're going to look at the exponential decay function. We're going to look at 1/2 to the x. I'm going to use the same x values that I used last time, just to kind of see what happens. And so I'm going to start with anything to the 0 power. So if I plug in a 0 for x, I would have 1/2 to the x, which is just, 1/2 to the 0, which is just going to be 1, because anything to the 0 power is 1. 1/2 to the first power is just going to be 1/2. 1/2 to the second power, we are just going to square the top and the bottom, so 1/4. And so you'll notice that as we go further and further through, we're dividing by 2, dividing by 2, dividing by 2. And so if I was going the opposite direction, I would be multiplying by 2, multiplying by 2, multiplying by 2. So this is going to be a 2, and this is going to be a 4. And let me make my little tick marks. All right, and so I'm going to go ahead and plot these points. So -2, 4, right here. -1, 2, 0, 1, 1, 1/2, 2, 1/4. And so it looks very, very similar to the growth graph, except now it's decreasing instead of increasing. It's still never touching or crossing 0 into the negatives. So I still have an asymptote right here at the x-axis. If we look at our domain, so how far to the left does the graph go? The graph still goes to the left forever and ever and ever. So -infinity, and then it still goes to the right forever and ever and ever. The range, so looking at how far down again and how far up, well, how far down does it go? Just like the last function, the furthest down it goes is as close to 0 as you can possibly get. And so I'm going to put a 0 there. I'm just not going to put in equal to. The reason why we do that instead of starting with, like, let's say 1 is because it includes more than just 1 and up, because 0.5 is included, 0.25 is included, 0.01 is included, 0.0000, like you could do that forever. And so that's why we use 0, but then we just don't use our little equal to bar. Y is our variable for range, or f of x. I should be consistent. And then how far up does the graph go? Well, I'm following it up. There's an arrow, so forever and ever. And then our y-intercept, so where our graph crosses the y-axis, still at 0, 1. So the only thing that changed here is that instead of our function increasing, now our function for decay is decreasing. Okay, average rate of change. So it says you start out with a penny that will double every day for 30 days. Find the average rate of change from day 7 to day 14. Remember that this function has already been shown to be, okay, so our function that we're dealing with is this function. And they want me to find the average rate of change from day 7 to day 14. So this is going to be like my x1, this is going to be my x2. And so to find the average rate of change, you're just using the rate of change formula. I know my x1 is 7, and I know my x2 is 14. And so to find my y1, I'm going to take 7 and plug it into the function. So I get 0.01 times 2 to the 7th. And then I'm just going to plug that right into my calculator. And I'm going to do the same thing with 14. And I'm actually going to run out of time. So